week's high energy seminar. And this time we have Professor Xerxes Tata from the University of Hawaii. And he has been working extensively on searches for supersymmetry at the collider in recent years. And today he is going to talk about the Naturalness supersymmetry at the light Higgsinos. Let's welcome him.
Thanks. It's a pleasure to be back in Texas after so many years. I've never, as some of you know, I graduated from the other Texas, and this is my first time here. So today I want to tell you about naturalness, supersymmetry, and light Higgsinos. We'll see these each in turn. This has been work we've been looking at over the last year or 2 years. And Dan Mickelson is Howie Mayer student. Eza Mustafa was a postdoc in Hawaii now. And these guys have done most of the heavy lifting. The rest of us have been tourists. So we all know Susie solves the big hierarchy problem, that there is tuning to a part 10 to the 30 in the standard model. And if Susie is at the weak scale, that statement is true, and everybody in the world agrees with that. And the big hierarchy problem is that low scale physics doesn't have quadratic sensitivity to high scale physics. If the standard model were embedded in a gut, then the Higgs mass would be unstable, would get corrections which were of order m gut square. So m gut is the high scale physics. If the supersymmetric standard model were embedded in a gut, the Higgs mass in the supersymmetric standard model would not be quadratically sensitive to m gut square. M gut would enter only logarithmically. That is the big hierarchy problem. Okay? So all talk of naturalness of weak scale Susie talks about the logarithmic sensitivity to the high scale. I've called the high scale as lambda in this talk. If it was a gut, then lambda would be a gut. And much discussion has revolved around this formula for mz square, which is almost a standard formula in the Susie book, except for these things, which are radiative corrections. Okay. So these sigma d and dd and sigma uu are radiative corrections, and otherwise this is a very standard formula. And notice that there is a tan squared beta minus 1 downstairs, which means things to do with the down Higgs don't matter very much, because tan beta is probably 10 or 20 or something. Because of this suppression, they don't matter. So mz squared is a cancellation between this guy and this guy. Okay? And so what we say is, if there is a model which should not be fine-tuned, there should not be very large cancellations between this term and this term and this term. None of these terms in magnitude should be much larger than mz squared. Otherwise, there would be unnatural cancellations. And so we define, and since these are all electroweak scale parameters, we define delta E electroweak as the maximum of all these terms. Okay, that's just the definition. And we'll see whether it's a good definition or not.
So in some sense, this is a bias that we think things are likely to be that way. Is that right?
No. What we are saying is, if mz squared is a plus b,
yeah.
What I'm saying is a and b both should be of order. Mz squared is an output. A and b are inputs. If mz squared is a plus b, I can always adjust a and b to get mz squared. But if I had to adjust a and b, if both of them were 10 raised to 30 and b was minus 10 to the 30, I could still get mz squared. That I would call unnatural. It's not whether it would be likely or not. If my theory...
But it's a bias that's unnatural in some sense. It doesn't have to be that way. Nature could be that way.
Yeah, right.
It's just a bias.
Nature could be that way.
It's unlikely to be that way, so let's start.
No, I don't even know whether it's unlikely, but we are defining naturalness to be that way. If you had to, because these would have to be cancelling to 28 places of decimals or whatever, that we think it could be that way. Yeah. In fact, Sandeep, my colleague, always tells me that I'm talking shit because he says it could be that way. There's only one nature. So That's true. It's not a logical
So
problem.
it's not a natural definition for naturalness.
Some people
I'm
nature,
sorry. that
nature
was
may not be natural.
Right. Nature may not be natural.
nature may not be natural in this way. Yeah, logically there's no problem.
Okay.
I
understand
absolutely
what you're
agree.
saying.
I absolutely agree. Okay. This delta electroweak that I defined knows nothing about the high scale physics because it was all written in terms of electroweak scale parameters. But if I have any theory input, it usually is coming from some sort of high scale physics. So for example, the weak scale MHU and MHD were the gut scale values plus something else which came from renormalization group running or what have you. And the logs that we talk about, the large logs that we talked about are sitting in here. This is the renormalization group running thing. Okay? And so if there were cancellations between this and this, if this depended on some other parameters than this, if there were cancellations, that would still be unnatural by the definition I gave. Okay? So delta electroweak in that sense was not a good, even though many people use it, I would have said is not a good measure of this sort of high scale physics. And so we can define delta high scale analogously, including writing the MHU square and MHD square in this fashion, and requiring each of these things be small. And that's a very, very high standard. Almost in fact, no theory that I know of meets the standard, even though I would love it to meet the standard. And we're going to talk about that in a second. Okay? But there is one thing that this is missing, this high standard is missing, is if we have a real theory, say M-Sugra or something, it has very few parameters. Okay? And it's very possible that all these quantities, because the theory has few parameters, all these quantities were not independent. If they are independent, then this is the correct definition to use. If they are not independent, this is not the right definition to use. Okay? So that's what I call correlations. That the different terms may automatically be correlated in many theories, in many models. And then we have to have to modify our definition to take these correlations into account. And what I mean by that, so for example, if I take the MSSM and calculate this delta MHU square, or MHU square as delta MHU square, on the right-hand side, I have written terms all at the high scale. There's some horrible-looking approximate formula, which is the integration of the RGE. These funny coefficients are the integrations of the RGEs. But now if I had a theory like M-Sugra, which says, for example, all the scalar masses have to be common at the high scale, this horrible-looking thing compresses to this. Okay, this is true in M-Sugra because of the correlation between the parameters. And then now you see, if I change M0 square by a little bit, because of this small coefficient, MHU square will hardly change. So this thing becomes stable, right? Because of the correlation between parameters. And that's in fact what people have called the focus point region. Okay? And similarly, we could do this for MHD square and so on. So we have to take these correlations into account to have a sensible definition. And the easiest way to take them into account are by what people have called the Barbarian-Judicial measure, which gives the fractional change in mz square as an output, divides it by the fractional change in your independent input parameters, and take the maximum of this guy over all the parameters. That's defined, that's the usual definition people used. Barbarian-Judicial, they call it the Barbarian-Judicial definition. It was actually introduced by Ellison Kuzmanopoulos as well, before Barbarian-Judicial. So I've given you three different measures. One was in terms of purely electroweak, which knew nothing about logs. The other one was the delta high scale, which was too stringent. It didn't know about the correlations. Delta BG was in between. And I claim it, and we'll have an inequality like this, because if there were logs, this thing would be fine-tuned, and this guy didn't know about them. It didn't take that fine-tuning into account, so we get this thing. And delta BG takes into account correlations, so delta high scale would overestimate it when there are correlations. If there were no correlations, these things should be similar. And in fact, you can see that these things, the BG and the high scale, are very correlated. This is the high scale, this is the BG. Nothing equal, they'll be correlated, so they go along one line. Except in M-sugra, there are a bunch of points where delta high scale is much larger than delta BG. This is exactly the so-called focus point region, where you expect delta high scale to overestimate the fine tuning.
Remind me when NUHM2?
NUHM2 is the same as M-sugra, except the Higgs masses you don't take to be M0, you treat them as independent parameters, the high scale Higgs masses. So non-universal Higgs model, HM is Higgs model.
So all of those are going to be much higher typically than the light?
These are the gut scale, no, they need not be, they can be higher or lower. But just that in M-sugra, you take all the scalar masses to be the same. In NUHM, you take all the matter scalar masses to be the same, but the MHU square and MHD square, the gut scale, you treat them as independent of M0.
So I know we think the M-sugra much more constrained.
M-sugra is more constrained.
But the point visually, the M-sugra has more points,
More points?
the more area.
No, this is nothing to do with it. It depends on how many points you have generated. You have no idea how many points there are on this.
Okay.
Right? So,
Okay.
yeah.
There you are.
It's not the area, it's just
No,
a.
I see.
Okay. So I gave you these three things, and then you can ask, the fine tuning had everything to do with the logs. Your delta electroweak didn't know anything about the logs, so why should I care about delta electroweak as far as fine tuning goes? And what I'm trying to tell you, the logs are in here, but imagine we had a theory, some fancy high scale theory, where the correlations were such that this guy automatically canceled this guy. Okay? I don't have such a theory. There are examples, partial examples of I don't have a successful theory like this, otherwise I'd be talking about that theory. But if this guy automatically canceled this guy, then this combination would be, there would be no logs. That's what I mean. The logs would automatically cancel. And then this thing which measured delta high scale numerically would become the same order as delta electroweak. Okay? In that case, delta electroweak would become a sensible fine-tuning measure. This happens, as I said, most familiarly in the so-called focus point region of M-sugra. Okay? People have touted it as a non-fine-tuned region. I don't agree with that, but that's a different story. In the NUHM2 model, MHU square is independent of the other parameters. So in principle, I could always adjust this to cancel out this. So I can always find a solution. I think that such a solution is fine-tuned because you're adjusting something. Okay? Some of my collaborators disagree with me, as we'll see later. And so anyway, we can find examples where these things cancel, and then we have to talk about those examples in a second. But let me talk about some properties of delta electroweak. First, it depends only on electroweak quantities. Doesn't care about how superpartners got their masses. So essentially, delta electroweak is determined by the spectrum. Secondly, I told you we have that inequality. Delta high scale is bigger than delta BG is bigger than delta electroweak. So if delta electroweak itself turns out to be large, your goose is cooked. The theory is fine-tuned because the other guys are even bigger. And the fine-tuning is inverse of these deltas. Okay? So if delta electroweak is large, you go home. You say that this theory is fine-tuned, for sure. If delta electroweak is small, you cannot say this theory is not fine-tuned. So delta electroweak is a necessary condition, but not a sufficient condition for fine-tuning. And if you remember the formula for delta electroweak, I should have mentioned this before. Oops. This delta electroweak is the maximum of these individual terms. One of them is mu square. So if mu square were way larger than mg square over 2, this would be fine-tuned, right? So delta electroweak small means mu square should necessarily be small. Okay, keep that in mind. Mu square needs to be small. And since this delta electroweak is determined by the spectrum, many aspects of the phenomenology are also determined only by the spectrum. So even though I don't know how the spectrum came about, if I'm given a spectrum, I can figure out what delta electroweak is, and I can say that spectrum is for sure fine-tuned, or may not be fine-tuned. Because if I calculate delta electroweak, if it's large, I don't care how that spectrum came, but there's no way the spectrum may not be fine-tuned. So in that sense, this is very useful. It tells you that certain spectra are no good as far as this fine-tuning goes. And we think that low mu that I just talked about is more fundamental than light stops for reasons you will see shortly. In that we can find models with light stops where delta electroweak is small, but if mu were, I'm sorry, with heavy stops where delta electroweak is small, but we can't find, impossible to find models with large mu where delta electroweak is. So how do we realize this small delta electroweak? As I said, the most important thing, these D-type Higgs terms are not important because of the tan squared beta. So the most important thing are the up Higgs sector and the mu. Okay? Those are the two messages. And in the NUHM model, where the Higgs masses are independent, I can always adjust this up Higgs mass to get a small weak scale Higgs mass. Okay? Keep that in mind, because that's an independent parameter, the high scale. And so I can always adjust it to cancel. So, and we'll see how we'll use that. Again, getting small delta electroweak is not an empty statement, because if you take a model like like M-Sugra, in M-Sugra, if you scan the parameter space consistently with the phenomenology, the minimal value of delta electroweak comes out to be a couple of hundred. Okay, so I would say that M-Sugra now, with the data at hand, is definitely fine-tuned. Okay. The main contributions.
Say that again. So if Sugra is correct, then it has to be fine-tuned.
If Sugra is correct, yeah, consistent with the current bound.
So in other words, you would need fine-tuning to have M-Sugra still be viable.
Yeah. Or what? Yeah, or more technically, I would say that M-Sugra may not be the underlying theory, but any theory that becomes M-Sugra, that leads an M-Sugra spectrum, will necessarily have fine-tuning. Because delta electroweak is large, so the real delta BG that you would have used to measure the high-scale fine-tuning is even larger. Okay, that's a logic. So, to get small delta electroweak, we have to get a small weak scale Higgs mass. We have to make sure these radiative corrections are also small. The radiative corrections to the up Higgs mass. And these guys is where the stop enters. And out here, this is for M-Sugra, but the same picture holds for NUHM. I've made a picture of the plot of delta electroweak versus A0, the trilinear parameter as measured in units of M0, A0 over M0. You notice that delta electroweak is pretty large, 50-ish, and has a sharp minimum at A0 equal to minus 1.6 or so M0. Okay, it has a sharp minimum. This is quite generic, even though it's for this one point. I've shown it. For the same value of A0, you get large mixing, and the Higgs mass goes up to the value we would like. So the same A0 seems to solve two problems. But you might say, hey, you're fine-tuning. And yes, I am. I would say that. So, what I'm saying is not that the NUHM model is not fine-tuned. It does give small delta electroweak. Right now, I'm not saying that this model is not fine-tuned. But if the NUHM model came from a model that somebody else, some really smart guy wrote down, where that model, I call it the meta theory here, predicted that A0 had to be around this, and NHU squared had to be that. That's also another thing that we need. I didn't show it to you. Then that meta theory would not be fine-tuned. Okay? That's the message I want to give. I'm not saying that this model is not fine-tuned. Is. Yeah. Okay? So, and in that theory, the high-scale fine-tuning measure that we used is delta BG. Incorporating these correlations would automatically, numerically become equal to delta electron. Okay? And then, like, is the right measure. So, So this is something we have just been doing in Hawaii. In fact, the Oklahoma people don't know about it yet. I just sent them the talk. So we had this analysis. We had in our old papers a couple of points which had low delta electroweak. Okay, this happened to have some point with delta electroweak around 11. It had a very large delta BG. So I would have said this point is fine-tuned if you took the NUHM2 as the underlying theory. But now, if you put the correlations that we just talked about in, A0 equal, it should be minus 1.670, and MHU square equal to that, and recalculate delta BG, it'll change because of the correlations. It changes by an order of magnitude. If, in addition, you put the correlation that M1/2 is 40% of M0, 400 is 40% of 2500, the delta BG becomes 15. So that's the illustration that I want to make, that the correlations automatically reduce delta BG down to delta electroweak. Now, to get these things is very hard numerically, because something which started off at 3000 has to become 15. So you have to calculate each individual term correctly to a percent, because these cancellations have to happen automatically. If you screw up your calculation numerically, you won't get it. And these are very hard calculations to keep numerically stable, because you're solving the 26 RGEs or whatever the hell the number of RGEs is. So this doesn't look like it's completely saturated. It may not have completely saturated, or it may have, I will not know, because our calculations are not that stable. And we've just begun to look at this. Okay, but this is what I mean by saying correlations can automatically reduce delta BG down to. So all somebody has to do is to find a high-scale theory, a meta-theory, with these correlations in. And that meta-theory will be not fine-tuned. To make sure this was not an accident, we checked this for a second point, and there were similar results, a couple of order of magnitude cancellations. Okay? So it's the meta-theory which is not fine-tuned, but the NUHM2 is the low-lying effective theory, and that you cannot tell anything about. All you care about is the ultimate theory. Okay. So, to recap the utility of delta EW. I would say it's not a fine-tuning measure. In fact, I said that in the previous slide, which I went over, but it is a bound on the fine-tuning measure, as I've been saying. This statement, how he told me to write, may say that some of your collaborators do not agree, so truth in advertising, I have said it. So, okay. So delta electroweak is essentially determined by the spectrum. So Teruki and his friends go measure the spectrum. I will tell them, look, your spectrum could not come from any non-fine-tuned theory, or it has a chance. Okay? So that's what I said here. And low mu is very essential for getting it. Low mu, we can find low mu models where squarks, including stops, are quite heavy in the TeV range. But mu is small and delta electroweak is small. Okay? And since many aspects of the phenomenology depend only on the spectrum, I can even talk about the phenomenology of this without knowing what the underlying theory is. Okay? And that's what I'm going to do in the next class. And so I emphasize that we think low mu is a necessary, more fundamental feature than light stops, which have been emphasized in the literature, because stops are the things that the LHC likes to look for. And I would say low mu correlates with light Higgsinos. So light Higgsinos are a more generic feature of natural models.
So let me make sure I understand what you're saying. So if you're going to protect the Higgs mass in some sense, you're saying that you might not find any squarks or even stops at the LHC because they're very light, and the only thing
They're very heavy.
They're very heavy, but you would have a light Higgsiano.
You would have light Higgsinos, and whether we find it or not.
Yeah, whether we find it or not. But in some sense, what really matters is that mu is low, and that's why we predict.
That's right.
So in other words, we might not have light stops, but we
Right.
still might have low scale SUSY.
Right. So guaranteed, I would say low mu.
Low
There is
mu.
a caveat along that goes along. It's a technical caveat of translating that to light Higgsinos. We can talk offline about
So it
it.
doesn't mean that the low mass particles are there, it's just that mu be low.
Mu should be low.
Mu
And
should
in
be low.
all models that we know, low mu means light Higgsinos. But there's a technical caveat that goes along with that. But
Right,
that's
and like
not interesting to
Higgsinos,
talk
which
about.
you gotta help us how we find those,
Yeah,
if there's
yeah.
nothing else producing them.
So we're going to talk about light Higgsinos a lot in the rest of the talk. Okay?
Does it take like this?
Yeah. Okay, so to get delta EW, low delta electroweak models, this is just a technical slide, how to generate them, but that may be not so interesting. But the features of the spectrum with small delta electroweak are light Higgsinos, neutralinos and the Judicial. Stops are typically in the TeV range. Even the light stop is 1 to 2 TeV. We found it very hard, at least generating them this way, to generate a lighter stop. And the gluino can be as heavy as 5 TeV, in which case LHC is not going to find it. They may find it in the bottom part of this range, but LHC may not find, what I'm trying to say, LHC may not find stops or gluinos, and still delta electroweak will be small. And this has nothing to do with low CP. The first two generation of squads could be 10 TeV, and they won't affect the smallness of delta electroweak, but they would help us with flavor and CP problems. So in a way, for doing phenomenology, we find this type of thing may be more interesting than models that we've been looking at. So since I've been emphasizing light Higgsinos, let's talk about phenomenology with light Higgsinos. So these states will be light, and generically the mass splittings are small if the other states are heavy. That's because everybody has a mass close to mu. And of course, if M1 and M2 by coincidence happen to be light, then it would be very easy to find. I mean, we would have enos coming out of your ears at the LHC, and also easy to see because the mass splittings would be moderately large. But that's a happy circumstance. The generic case is the small mass gap. There's a novel signal at the LHC, which I will talk about, and of course, electron-positron colliders that can produce these Higgsinos, because Higgsinos now are at a couple of 100 GeV range, will be the natural place to look for them. So let's talk about the LHC. And for convenience, I've taken a unified Higgino mass M1/2 and plotted out cross sections versus M1/2. Whole bunch of cross sections. The gluino cross section is the red one, and of course, as M1/2 increases, it rapidly drops. These are the Higgsinos cross sections. Since mu is fixed, the Higgsinos mass is fixed, so it doesn't change. So Higgsinos are the dominant things that are produced. That's a no-brainer. I mean, you didn't need a plot to see that. Now, if M1/2 is somewhere in here, then the Chargino cross-section and the Chargino neutralino cross-section, W1Z4, the Wino cross-section, basically, the Wino cross-section, okay? So W2, W2, and W2Z4. The Wino cross-sections are the diamonds and the crosses. They are big, because you know Wino cross-sections are big. And if the Wino cross-sections are in this range, there would be enough production at the LHC, and then you get a novel signal. It's not 100% guaranteed, but if these guys were produced, the charged Wino can decay into the lighter neutralinos, 1 or 2, and a positive W. And the neutral Wino could also decay into a positive W and a lighter Eno. These guys, remember, have a very small mass gap. So when they decay, the decay products are very soft. So you get some piddly jets, but they're not your garden variety jets. So let me pretend that these guys were piddly. In that case, what you have is W plus with limited hadronic activity. Okay? And I
You
claim,
still get missing ET.
sorry?
So you get four jets.
You get missing ET.
So you get 4 jets with missing ET, where the 2 jets are where the
Well,
pairings
yeah,
give you
so
W
I'm going to
pairs.
focus on the leptonic decay of the W. Or you could look at 4 jets plus missing ET.
Okay, so the
But
mass.
4 jets plus missing ET would be confused with supersymmetry from Xerxes.
I can live with that.
You can live with
I
that,
can
but
live
here
with
we
that.
agreed.
No, but what's different is that if you're looking for, you will have mass pairings that give you very
have mass.
definite masses, which is very useful. And it would be very different than the gluino, square
Absolutely. I
gluinos,
agree.
which would be much more cascade-like.
Yeah.
This would be
Absolutely,
very
I agree.
symmetric.
We haven't looked at that.
All right, what masses are you thinking about for W2Z4? Those are
W2Z4, 5,600.
5,600s.
Where you
So
will
what
see
about
where
Higgs?
you will see the signal. These guys are 100, 200.
So why wouldn't Higgs decays be in here? So like when you start getting these guys.
Oh, no, some of these guys will also decay to Higgs. We are looking at a particular thing with the branching fraction because we think this is the best signal.
Because I would guess if you had Higgs decays in there, they would
And
show up
then
as
Higgs will decay
BB
to
bar.
Yeah, you might be
BB
able to
bars
record
stick
it.
out like
Yeah.
a smoking gun.
Yeah. Well, I don't know. Well, I don't know which is the best way. We focused on this. There are a whole bunch of them.
BB bar with a mass of 125 plus missing ET.
Yeah, so long ago, 15 years ago, we have been pushing for seeing Higgses in that way. But here we didn't look. I think it's harder. I'll tell you why it's harder offline. Because we looked for a different study, we looked at that, and the signal was harder, I thought, to pull out.
Yeah, well, right.
Okay.
We haven't said anything about what the backgrounds are.
Yeah, so we did some backgrounds, yeah. Okay, so as we said, same sign W backgrounds. In the standard model, they can come from 2 to 4 processes, which these gentlemen had estimated. They can come from double parton scattering. In both these cases, the missing ET is relatively limited, whereas in our case, the missing ET is large. Okay, and these are not a problem. TT bar could be a potential background if the second same sign lepton was accidentally isolated from B, but this is generally jetty and it's not a big problem. Okay, we've done this with simulations. So TT bar W is the biggest physics background from the standard model, but again, it has extra jets from the T's, and so I'm going to show you that it is controllable. And these are backgrounds to the same sign W if you miss something. These are the reducible backgrounds. Okay? And we did a study of that. We did a study of the backgrounds. And here is the answer versus M1/2, fixing the Higgsinos masses at 150 GeV for the CMET. We put a missing ET, there are 2 sets of missing ET cuts, one with a dash line, 2 with a solid line. The dash line has missing ET bigger than 75, the dash line has 200. This line is supposed to be for low luminosity running, low luminosity meaning 100 inverse femtobarns. Both of these are for LHC 14, and this is for higher luminosities. So if you're less than 100 inverse femtobarns, a more modest missing ET cut, along with a very crucial cut, is the transverse mass cut. An MT2 cut would work as well. But we've done a transverse mass cut on the missing ET and the leptons. Okay, to take out leptons from an on-shell W, because they would be devastating. Standard model on-shell W. So that gets very effectively removed, and we can, even with 100 inverse femtobarns, we should be able to probe M1/2 beyond 500 GeV, above the background that I just told you. And if you had high luminosity LHC, you should be able to go out almost to a TeV. We found this rather exciting because the reach in this channel is bigger than the canonical Gluino search reach from multi-jets plus missing ET if you assume Higgsinos mass unification. Right, because we've used M1/2, so Gluino mass is fixed. So this gives you, for a luminosity bigger than 100 inverse femtobarns, this channel gives you a bigger reach if Higgsinos are right. Which, I mean, was a surprise to us, but it's true. How about the canonical trilepton channel? This channel, I can take you through this in detail. I probably won't because I'm running out of, going slower than I expected. If you go through this, you find that in this case, and the trilepton channel is something dear and close to my heart, but even then, I would have to say that in this class of models with low mu, the reach in the same sign W channel is smaller than the reach via the canonical trilepton channel. Okay, so I won't take you, so these are the signals in the backgrounds, the reach in the trilepton channel. The other thing is that in these low Higgsinos models, the 4-lepton channel gives a surprisingly large reach. It's not as large as the same sign dileptons, but it is comparable with the reach in the trilepton channel. Okay? And so this would be a fantastic confirmatory signal. So the reason I'm pushing these is if you didn't have light Higgsinos models, the same sign channel and this 4-lepton channels don't give you as big a reach. If you see things like this, where the same sign W channel is big, so same sign dileptons, which are not jetty, is big, to me, I would be very tempted, aside from R parity violation, to say that something is happening with light Higgsinos. It would point me to light Higgsinos, and then I would go and look in confirmatory channels. Okay, so this is a way of distinguishing the canonical thing that we've been doing, let's say M Sugra or whatever, where mu was big, to where mu is small.
But Xerxes, suppose I have mu big scenarios and then I produce lightest Higgsinos or second to lightest neutralino, and there is a
So that's a Higgsinos.
yeah, that's a, and there is a lepton in between, and then you can get
You won't get four.
4 lepton channel,
Oh.
and neutralino 2 decays into 2 lepton because lepton goes to neutralino 1, and you can get 4 lepton.
Oh, yeah. So then you need another light lepton.
Yeah. So,
But
so
the
that
light,
means,
I think if there was a light lepton, we would probably know it in a different way, right?
how? That's
By looking at the Drelian light leptons. Up to 400 GeV is easy, I think.
So the bound is very tough.
Not at present, but with LHC 14.
Even then, what's happening there? If the lepton and the Drelian chases lepton with a lepton neutralino mass difference to be at least 100 GeV or so.
Say again? Drelian.
Like Drelian puts constraint on lepton mass if
there should be a reasonable mass gap,
differences were huge,
Yeah.
quite big, like at 100 GeV or something like that.
I don't remember the number.
Yeah,
but
so
it-
because
yeah.
we had, and that scenario could be potential background to you. Like if you see I don't know how to distinguish.
Yeah, I haven't thought about that. Of putting a lepton light in between. I
Yeah,
haven't.
like.
So, no, you don't even need, in principle, you don't even need a light lepton. What you would say is because 2 neutralinos.
Yeah.
But if
Exactly.
one were going into,
Neutralino to lepton goes to lepton neutralino.
Yeah.
And also maybe you can, even if you don't need in that case, okay, that suppose it goes via Z, but of course then
No, but then the
dilepton
Z will
mass,
be on
yeah,
shell.
yeah,
Z will be on shell.
then on shell, then you can figure it out. But light lepton probably would.
yeah, but light lepton, if the Z channel is open, the light lepton channel has to be also open for it to be competitive.
Yeah, but, suppose.
Then probably the Z channel is also open.
Yeah, well.
The Z channel has, lepton is not lighter than the Z.
No, yeah, so for what happens if lepton is open and then neutralino 2 would go to lepton more often?
More often, but
Because,
you will see some fraction going
very
to
little
Z.
fraction of.
No, but I mean, seeing that, you will know that
Yeah.
this is happening. I don't know, but we haven't thought this through. Fair enough. Okay. Oh, so this is for 4 leptons. These are cuts, and to a missing ET cut is very good to pull out the signal. That's not news. And so here is a table with a bunch of cuts. Again, I don't think I need to take you through the table, but the point is that if Higgsinos were light for a reasonable mass range, depending on the masses with 2 different analysis cuts, it is possible to pull out a signal with 300 inverse. This is with 300 inverse vector bonds. So the 5 sigma signal comes out somewhere up to 550 or so, in 1/2 of 550, which is pretty large in 1/2. Okay. So then we wondered that if you're producing these light Higgsinos, is there any chance of seeing the light Higgsiano thing, even though the decay products are soft, because the cross sections are so big? We tried to do very soft lepton cuts with, I think, electron bigger than 10 and muons bigger than 5. We tried to do an analysis, and basically we found that unless M1/2 was really small, you could not do it. The best way to do it was to look at the dimuon mass distribution. I haven't shown that to you here, and look for a distortion in the dimuon mass distribution. Harvey is more optimistic than I am about it, but I'm a curmudgeon, as he keeps telling me, and I never see a signal even if it is in front of me. But if M1/2 were very light, then at low mass you do get some distortion, but otherwise I think it is very tough. Even though in principle you get 5 sigma, the signal over background is tiny. So at least I don't believe it. Then the other thing which is fashionable these days to do was to look for monojets or monophotons. Because you produce Higgsinos on one side and radiate a QCD jet on the other side. And there was a Chinese paper which said this is not the Han we know and love, but a different Han et al. So don't go around complaining to Tata that I pissed on him.
No.
It's a different Han et al. And the problem with the monojet signal is, so these were a bunch of backgrounds from Z plus jets, W plus jets, and this was the signal. It's way down up to PT jet, which is almost a TeV. To me, this looks unpickable. The Chinese had written a paper which said it was pickable. Then they had version 2, version 3, which supposedly was accepted for publication. And then they told me to look at their version 3, and they looked at the version 3, and they had screwed up on the systematic error, totally screwed up. I mean, there was no, and they have agreed that they had to put out a version 4, saying you can't see the signal. So at least the Chinese and us are in agreement. So if I look at these LHC reaches in the various channels that I've shown you and not shown you, as a function of, and look at our projections within this class of models with light mu, they cannot, if you had only 10 inverse femtobarns, you can't see any of the fancy things. With 100 inverse femtobarns, the canonical Gluino search, remember squats are very heavy, and the same sign W search give comparable reaches. And the 4 lepton, maybe you start picking up something. And as you grow up in luminosity, this guy beats this guy, and there are confirmatory signals in other channels. And I think that if physics is this way, we will get a good clue that physics is that way and won't be confused for other types of physics that Pascal's been saying, whether or not. It's nice, it'll be nice to see some new physics anyway, but then we can disentangle it. And I think there's a good chance that we'll be able to. So this is what I call the propaganda plot. M1/2 mu plane, because we are talking about things with light mu. So these red things are contours of constant delta electroweak. So if you say you can stand at most 3% fine tuning, delta electroweak should be less than 30, so you'll be in this region. The green region is what is cosmologically allowed by the statement that the neutralino relic density should not exceed the observed relic density, it may be smaller. So you are forced to live in this region. If you take delta electroweak 30 to be the 3%. LHC in the Gluino channel would probe this with the same 300 inverse femtobarns, with the same sign W's probes a little more. But there is this part of the region which would not be probed. Okay? And LHC 3000 probably won't go much more than this. I mean, it'll go incrementally more. A linear collider, assuming you could see such signals with small mass gaps at a linear collider, would probe the entire region. That's why I call it the propaganda plot.
What if you didn't, if you added the constraint that the Higgsinos is some sizable fraction of the relic density? I mean, if we're calling it less than 100%, clearly buys you something, but if you said it was between 50 and 100%, I mean, don't get me wrong, I like the idea.
Yeah, I don't know. I don't know how the green region would change, but
Yeah.
how much I don't know.
But which way would it, would it shrink in that way, would it
The
shrink in
smaller
this
The
way?
green region would reduce. Green region would become smaller.
No, but which way would it reduce? Which way would it shrink?
Whether you mean whether it will go this way or what other way? This way?
All right, so you have the white region, which is encroaching. Right.
No, the green region is a good region, right?
Right, but so I presume that the boundary between the green and the white is the boundary where you go from 100% to more than 100%.
Yeah.
So if I went from, it had to be 0% to 50%, would it come in from the other side? And so you'd be basically getting a diagonal band?
I don't understand. So Higgsinos does a weird thing. So Higgsinos cross section is huge, and so what it does, it reduces the dark matter.
Yeah.
So
The
it doesn't-
Higgsinos are essentially the Higgsinos relic density is zero
Exactly.
around this side.
So Higgsinos.
So this side will not be affected, if that's what you're asking.
So
Oh,
Higgsinos.
sorry, this side will be affected, because you're saying you want Higgsinos to be remain.
But in some sense, what you're saying is that the dark matter is allowed to, that the Higgsino is anywhere from 0 to 100% of the dark matter.
Right.
If we said it was between 50 and 100%, it would, the green
I guess
region
the
would
answer is
shrink.
it'll go this way, but I don't know how much.
But it would go that way or it'd come in this way?
What do you mean come?
He means we should have some white on the right-hand side of the plot as well.
Is that what the, right, if I require it to be bigger than 0 or bigger than 10% of the relic density, then I should be,
Okay, Higgsinos of about 2 TeV, I think is the number, have the right relic density.
Higgsinos mass.
So that's in this direction. Higgsinos of 2 TeV, I think around 2 TeV, somebody can correct me if they remember later.
2.4.
2.4, okay, yeah, have the right relic density. I don't know what the 50%
well, but the
is.
right relic density is the assumption that
It's
all of
all-
the dark
it's
matter
all-
is the
yeah.
Higgsino.
And
But if,
below that, relic density becomes lower.
right, but it could be that there's Higgsinos and something else.
Precisely.
And what you, all
That's
you
something
said
that
is,
has nothing to do with supersymmetry, maybe.
Nothing to
Maybe
do-
actually.
no, but what you've done is you've assumed that it's anywhere, that the Higgsinos are anywhere from 0 to 100% of it. So if I said, if it was, you constrain it to be from 50 to 100%, which way does that plot get squeezed?
Okay, offline we'll figure it out.
Okay.
I'm sure we can.
I'm guessing it is gonna push this way.
So, but he assumed Higgsinos are 100%.
No,
No,
he said
no.
less than 100%.
Less than,
Less than-
less, 100%? No, 100%.
If it was 100%
Higgsinos
to
can
be a
never
point.
be, right? 200 GeV, Higgsinos can never give you 100%. It's less than, so all this region.
Right, this is the less than 100%.
This is all less than. So I think it'll come down from the top. The part that I, see, remember this Higgsinos mass is 600. As he said, 2.4 is the Higgsinos mass, which gives 100%. So all this guy has less than, much less.
So it
than-
might come down.
It might come down from the top. If that's what you were asking, I thought you were asking from the right.
Well, I'm asking, which way does it come in?
If
Right,
it
because
goes-
the region has to shrink as you constrain, and the
Yeah.
question is, which way does it
So
shrink?
this will go away and go out, I guess.
Yeah, go up. So
Yeah,
the-
you go up.
Go up because the lower mass means your smaller relic density, and then as you raise the mu mass.
But if it's gonna raise it, then
Exactly.
in some sense, that is saying that your Higgsino relic density, that the Higgsino density is a very specific fraction in that region, which is both
very small.
green
It's
and
very
less than
small in
30.
here. It's very small. in
It's a
here.
very small
Very small,
fraction.
Yeah.
What
And
fraction?
you'll see that.
Okay, okay.
It's
Yeah.
smaller.
It's a small but interesting fraction. Okay. Oh, in fact, it's right here. I didn't
Great
realize.
question.
Okay, right question. Okay, so talk about the dark matter in the relic. So the relic density in these low mu models versus the Higgsino mass is plotted out here. Higgsino mass from 50 to 350. Okay, so the green points are already excluded by dark matter experiments. So the red and the blue points are the ones where you have delta electroweak. The blue points are delta electroweak more than 50, and the red points are delta electroweak less than 50. So let's focus on the red points.
Remind me what a mega H squared dark matter is?
0.1.
0.1, that's the dash, that's the line.
That's the standard.
All right, so what these are saying is
Their
that they
density is
are
too small.
on the order of 5% of the dark
It
matter.
can go from
So if we
2%
discovered,
to 20% or 30%.
so if we discovered this Higgsino, we would have discovered 20% of the dark matter in the universe. Fine,
Next-
okay.
next-
And so you don't have
next-
any statement about what the rest of it is?
Yeah, exactly.
I don't have any, no,
Fine.
it could be axions, it could be some
Okay.
particle X, which has nothing to do with the price of potatoes, except to make dark matter.
This is thermal dark matter.
This is thermal dark matter only, yeah, no stories. Yeah, you would have to write another story, right?
So in some sense, there is no model where the dark matter that is consistent with this light, with no fine tuning that gives you 100% of the dark matter.
No,
No, you
yes.
can make a model.
Yes, non-thermal.
Non-thermal.
It would have to be non,
This is a
it would
thermal-
have to be non-thermal. Is that
It
right?
cannot be the thermal Higgsinos.
Thermal Higgsino.
It cannot be thermal Higgsinos.
It has
That's
to
the
be
same.
supplemented by axions, like
It could be axions, it could be some.
No.
So if there were no
non-thermal
other,
processes.
if there were no other of those particles, then you are left with the conclusion that either you are fine-tuned.
No.
No,
Non-thermal origin does not mean that you have new particles. There could
No,
be-
I would have to introduce some new field that decays, for example, into a Higgsino.
Exactly, long time back, so you may not see them.
You may not see anything now. The dark matter may be all Higgsinos, but
But
produced
back
not
then it could be
thermally.
something else.
Not
Also-
produced, no,
also-
not produced thermally.
Also axions, like it's different.
No, but the point is that if I were to say there are no axions,
Yeah, if you say that,
if I say there are no axions,
Non-thermal, then.
non-thermal or a new particle.
no, but if I said there are
There are no
no
other new particles,
Yeah.
not only not axions.
right, not only no other new particles, not axions,
Then
that
not,
provides a very remarkable, that provides
Yeah,
a
but
very
I-
serious
That's a pretty
constraint.
ballsy thing to say.
Yeah.
I'm at,
You
well, the
leave
point
it.
is that it would push you
yeah.
outside of your non-fine-tuned region.
Yeah, that would, yeah, but if you make enough, there are many ways of pushing us out
But
by
the-
making theoretical
To
assumptions.
prove that, probably you'll retire by then.
No, but in some sense, what you're saying is that either there are new particles other than the Higgsinos, which are dark matter, or nature is not, could be fine-tuned if it's the only.
Sorry,
So
I should make another very important caveat. All
I mean,
the
that's an
ana-
important statement.
No, but all the statements I'm making have been under the assumption that my SUSY spectrum is MSSM. The moment I go to NMSSM,
Things-
many statements change, okay?
All this fine.
So that's a much easier way of changing things.
But I think he's saying that you don't see any other particle, so he's kind of trying to understand this fine tuning more than anything
I mean,
else.
in some sense, something,
I think that's-
what we're saying is that something's gotta go. So it's either the fine-tuning or it's the MSSM, right? So if it's MSSM, then we have fine-tuning.
That's right.
You get one or the other. And if you
Or-
say it's
so
NMSSM
if you
or
know it-
axions or something,
if it is
then
no
you can still have
MSSM.
fine-tuning. You have no fine-tuning.
If
But
you
it-
have nothing else.
Right,
But
but that
that's a
something
very
else
hard-
also has to be giving you the dark matter.
Yeah, but.
Also, axions could be part of MSSM, so.
Well,
you
axioms
said
are not
QC
MSSM, right, but.
Yeah, QCD vacuum, so.
Yeah,
you don't
so
know
you have
what
to, yeah, you have to put in the axiom, but,
So MSSM means I don't know what's MSSM.
But if,
means.
all right, but if SUSY is providing all of the dark matter, then it
Yeah.
has to be an NSM. It cannot be MSSM.
Or non-thermal MSSM. So I don't know, like, because non-thermal, because the moduli is, so if you.
Or
say
we have to
that-
have high
Yeah,
fine-tuning.
MSSM arises from string theory,
yeah,
moduli.
if
blah,
there are
blah, blah,
moduli,
you
some
can-
fields which we
Yeah.
we will not see today and we will
Exactly.
never see in the lab, but they decayed into.
Gravitationally to this sector, MSSM, blah, blah, blah.
There are many
and then
stories you can
Many
do.
stories I can build for you.
You have a question? Oh, I see.
He's stretching.
Oh, it's stretching. Okay,
I think he was throwing a flag, actually.
as long as it's not a tomato, it's okay. Okay, on the right-hand side plot, which I found more interesting, by the way, these plots have come from Baer, Barger, Michelson. If the dark matter is some fraction C of it, well, say 10% is Higgsinos, then, of course, the cross-section limits will apply will go down by the corresponding fraction, right? So the scaled cross-section versus the Higgsinos mass, the present searches are out here, but what you see is with xenon 1 ton, even though the cross-section may have reduced, the xenon 1 ton will see some signal of these Higgsinos if it is not fine-tuned. That I found surprising. And that comes from the fact that this cannot be reduced arbitrarily. And the reason this cannot be reduced arbitrarily, that you need some Higgsinos part of the wave function, is your gluino in these scenarios could not become too heavy. Because if the gluino became too heavy, the stops became so heavy so that the sigmas became, those radiative corrections became large. So it's a very tightly constrained thing. Assuming this 33% fine
So
tuning is the number.
only one comment regarding the spin independence. So the form factor has a large error. So
Yeah, the form factor error is not there. Yeah, I agree.
So it's difficult.
I agree, yeah. Okay, so can these things be detected at the ILC? So we studied 2 points. I mean, how we picked out a point where the gluino was just above the LHC thing. And I told them, I mean, this point is easy because there is a fairly big mass gap, 15 GeV mass gap. There's no way ILC won't find it. And sure enough, when we look for this, yeah, there was a 20 GeV mass gap in the neutralinos, 15 GeV for the charginos. You run it through. We worried about background from 2-photon physics because the decay products are soft. The visible energy will be very soft. And sure enough, so this is the 2-photon physics background versus the visible energy. So at small visible energy, where all the signal is sitting, the 2-photon physics dominates. The usual standard model 2-to-2 backgrounds have large visible energies. So you put a visible energy cut less than 50, and then you look at the missing ET in there. In that case, the 2-photon physics background goes like this. This is our signal, and this is the other background, which is small. So basically, missing visible energy bigger than 50 GeV, missing ET bigger than 10, and you can pull out, or in this case we choose 20, you can easily pull out the signal. And not only can you pull out the signal, there are enough events remaining that you can probably also do mass measurements in the signal. Okay, with 100 inverse femtobarns, to measure the chargino and neutralino mass from the chargino channel, you don't need polarization. For the neutralinos, you will need polarization. So this was the easy point. And then I had the job of pulling out a more challenging study. I said easy studies, will be obvious. So I went to one of our earlier plots and made the mass gap as small as I could, consistent with 3% fine tuning, delta L2V 30. And this was the point with the mass gap around 10. Because if you make the mass gap much smaller, the fine tuning becomes very large. And of course, the ENO masses went up a little bit, so we needed to go up in energy. So we went to the little below the top threshold, just to not deal with the top background. But I don't think the top background would be a problem. Again, look at the visible energy and missing ET. So the picture is very similar. The visible energy in the signal is even smaller because the mass gap was smaller. This is the 2-photon background, this is the 2-to-2 background, and putting a missing ET cut will, you might hope, find some way of pulling the signal, but it doesn't look good on that. But then Dan did even more cutting, namely on the opening angle between the jet and the lepton in the case of charginos, and he found that you can get a signal to background around 3 and without being polarization, and with 100 inverse femtobarns, that's very, very significant. Okay, and to see the neutralino cross section, you do need beam polarization, and again with opening angle cut between the leptons, you could get large signal to background. Signals are not big, but 100 inverse femtobarns is not a big integrated luminosity. So this gave me confidence that even this so-called difficult point, which I had been harping about, we could ultimately do. So I think with up to 10 GeV mass gaps, linear colliders will be a good place to definitively see Xerxes, even though LHC may not see a signal. So if linear colliders don't see this signal, then for sure I would say that delta electroweak is large, and so things are fine-tuned. So I will end soon. I've heard much about people saying that since LHC8 did not find Susie, Susie is dead. The same people 2 years ago had been saying, oh, of course, we need LHC14 to find Susie. So we have got half the center of mass energy and a small fraction of the design luminosity, and people have been proclaiming Susie to be dead. I think that's premature, and LHC14, at least I am certainly waiting to see what it tells us. For small fine-tuning, low mu is a necessary, but not a sufficient condition. So we should have light Higgsinos. And this delta electroweak, even though I say it's not a fine-tuning measure, I think it's a useful quantity because it can tell us for sure whether a certain spectrum is fine-tuned. And more than that, delta electroweak can be directly measured, at least in principle, if our experimental colleagues do their job. Light Higgsinos cannot saturate the cold dark matter thermally. And nonetheless, there has to be enough thermal fraction left over so that ton-sized noble gas experiments would see a signal. That's the plot I showed you from here. And I like this same sign di-electron signal with limited jet activity very much because it gives a completely different signal. And if Higgsinos masses are indeed unified, they may not be. In that case, the reach is better than the canonical reach. And finally, a linear collider with sufficient energy, if you take 300 GeV to be the limit coming from 30, the delta electroweak equal to 30, then a linear collider with 600 GeV energy would either rule the scenario in or rule it out. There will be no halfway point. So thanks very much.
So this lux and the electron is from 2W boson decay.
Yeah, maybe we will convince you that vector boson fusion can.
Yeah, so that I would love to be convinced. That's one of the reasons why I would love to be convinced on that, yeah. Because that would be, if this vector boson, we've been talking about it off and on, so I'm hoping it'll be more on while I'm here. And that would be a very nice thing to be convinced about, because then I would see the signal, and then we don't need a damn linear collider, which we may not get anyway.
And also 600 GeV, right? So far,
No, 600 GeV, I'm stretching things.
I know, like
So-
for example, we don't have the technology even for 600 GeV. Like 500 GeV up to that we have.
Right.
Right.
Yeah. No, but this is to make a guarantee.
Don't you want a top factor?
What?
Don't you want a top factor?
Yeah. So
I
500
thought LHC
GeV.
is the top factor.
Yeah. What else? How many top factories do we need?
I'm just saying.
Yeah, I know. But no, this is what. But really, I mean, Howie, for example, even says that I'm pushing mu equal to 300. That is too high. We should just say 200, and then it's very politically good to say that linear collider will find it.
Yeah.
So. But yeah, I'm sorry to have to say that M. Sugra, that is in this place, that M. Sugra was, at least according to us, definitely fine-tuned.
And also, I think Sugar is kind of, if you include all the constraints, I always say it's the first casualty of the.
Yeah, well, it was one of the most constrained things, so it's not surprising that it should be the first casualty. And in a sense, very few people took M. Sugra literally.
Exactly.
And it was a wonderful guide, I mean. for our
Wonderful
thinking.
guide.
It was a wonderful guide for our thinking, but
Yeah.
very few people took it literally.
If no more questions, let's thank other again.